Okay, so now let's finally get to Michael and his title, shall I say it? Diversity, equivariance, and inclusions.
Thank you. Thank you. Glad you went with that joke. Mainly because I realized that that's what I should call every grant that I fill out from now on. Because, and this is recorded, fuck everything. So I also like thinking of this as the third in a trilogy, which of course led me down an immediate rabbit hole of what would the other talks be titled. And so the first is clearly the Fellowship of the Ring Spectrum. The second, I feel like I should be something about The Empire Strikes Back. Just again to subvert things. And then ironically, for both, Return of the Queen works really well. So let's you're welcome. So let's get started. I'm actually talking about G-symmetric nodal stuff. And so I want to build on where we kind of ended on Tuesday. And so this is the theme that I've been sort of pushing this entire time, that I have an internal versus external form of a lot of the equivariant algebraic structures that we see. And the internal form for a Mackey functor was a product-preserving functor out of the Lindner category. And so this was the same data as a collection of abelian groups, one for each orbit, together with restriction maps that were contravariant, transfer maps that were covariant, and then an action of the Weil group at each of the positions. And they satisfied a formula that the Lindner category packaged quite nicely as a pullback condition, and otherwise it's expressing the fact that I can write the restriction of an orbit as a disjoint union of orbits. So the way I want to rewrite this is instead saying I had this functor from the core of finite G sets into coefficient systems. And this took a finite G set T to the coefficient system that I wrote as M sub T. So I'm fixing my coefficient system M. And the data of a Mackey functor was the same data as giving myself this coefficient system M and an extension of this functor from finite something sets and isomorphisms to all finite something sets. And you notice I did a little bit of a linguistic switch. I had been calling it finite G sets and isomorphisms, or the core of finite G sets, and then I switched to finite something sets and isomorphisms. And also I started underlining everything, which is the notation I'd been traditionally using for coefficient systems. So again, already I've switched sort of semantically to going from just coefficient systems as a category. Really, I'm thinking of coefficient systems as actually a coefficient system of categories, one for each of my subgroups. And I have restriction maps that connect coefficient systems for H to the coefficient systems of any subgroup. I have conjugations that permute the coefficient systems for conjugate subgroups. And then I also have a kind of transfer, but at the categorical level. And here, to say that I have this functor, it's to say that I have this assignment, T goes to M sub T, but it's actually compatible with restriction, and the same thing's true for my extension. So I want to build on this in several ways. So I want to see how I can package this in a more abstract framework. And then I want to also finally get back to the multiplicative solution. So the statement that I was making about shifting to the underline to the coefficient system version is exactly this one. That if I restrict my new coefficient system M sub T, this is actually canonically isomorphic to the I should have put parentheses in a different way to disambiguate. This is the coefficient system that's the restriction to H of M. And then I took that coefficient system and shifted it by the restriction to H of T. Everything I'm going to say about these follows very, very easily from manipulations in finite G sets. If I have a finite G set that's induced up, so G mod H cross something, like say some T, and I want to cross that with some other finite G set, then induction has this kind of absorbing property that G crossover H T crossed with some S prime. I can pull the S prime in and view the whole thing as induced. That's actually this statement, that I could have pulled the T in and view the whole thing as induced. And when I see that here, if I took for my operatic algebra X, that's an algebra for little disks in V, then the transfer that D of V structured, when I restrict that down to H, that's the same thing as the transfer that D of V structured for the restriction of T. So there's sort of this internal compatibility in all of this. It's just saying that I could have, if I was looking at something that was at the H level and it was the image of the restriction, I'm getting the same thing I saw as if I restricted the thing from the G level. So the other part about this that's when you first start thinking about it, and I gotta say this really confused me for quite a while, is that there's sort of an overdetermination for a lot of this. And you know, the way that Tompkins and I first sort of started thinking about the notion of a G commutative monoid, and we needed the categorical notion that I'll get to eventually of a G symmetric monoidal thing, then we knew that I needed this sort of coefficient system, which would record the data not just at level G, but also at the level for all of the subgroups. But then in practice, the information at the other subgroups was actually secretly recorded in the level G version. So when you write it down, like when I write down my operatic algebra, I actually just wrote down the G thing together with the operatic structure maps, ON plus tensor over sigma n with x to the n. I didn't actually write down a coefficient system of things. So it was hard to understand, how are these two things showing up at the same level? How is it that I needed, on the one hand, to keep track of an entire coefficient system of symmetrical categories? On the other hand, I didn't need to keep track of that. I just needed to keep track of what was happening at the G level together with some extra data. And so in the context of coefficient systems in Mackey functions, which is the main reason I've been spending so much time with this, we can actually make a lot of sense of all of these. Then when I look at what happens for an H set and the transfer associated to that H set, well, that Mackey functor and that coefficient system and map of coefficient systems is actually entirely determined by the one that I got when I induced up the whole picture back to G. So here, this is taking place at the G level, and now I'm looking at shifting the H set T back up to G using induction, and then G crossover HT maps down to G mod H via induce up the map T to a point. To see that this is actually a retract of it, well, all I do is think, well, let me restrict back down. And when I restrict that G set, G crossover HT back down, I need to think, how do I write G as an HH biset? Well, this is the double coset formula, and I want to avoid that. I never want to write it down. But there's one coset that I always have pretty good control over. That's the coset for the identity. H sits inside G. And it sits inside G as an HH biset. That's this whole first part. H sits inside G as an HH biset. So when I induce up T to H and restrict back down, that picks out a canonical copy of T sitting inside there. And if I applied that to T as a point, that would rebuild this map sits as a direct summand of the restriction of this. And it has folded in actually the other sort of bioconjugates and the restrictions of this to other sort of subgroups. So it records a little bit more, but in particular, I see this. And so even though 2 slides ago, I made a lot of hay about how, oh, I need to actually have all of this additional data of the coefficient system and record it in fact, here I don't. When I'm looking at the actual, the extensions of this over finite G sets, that's all I needed. It recorded for me all of the additional data. So it's a really helpful packaging. I like to think of this as kind of a Siegel or maybe better Shimakawa approach to this. That what I'm saying is if I forgot the G's everywhere, so I was just looking at finite sets and isomorphisms and abelian and sets, then a map, there's a preferred map that I want, I'm going to call preferred, from finite sets and isomorphisms into sets that takes a finite set T to M crossed with itself T times. So, or if you prefer functions from T into M. And to give myself a commutative monoid structure, and this is the part that's due to Siegel, to give myself a commutative monoid structure is the same data as giving myself an extension of that functor over all finite sets. The extension from, to give myself a unit is to say, how do I specify what happens to the map empty set to point? Because crossing with the empty set, that gave me just a point, or hom from the empty set was a point. And then to give myself maps from point into M is just M. So when I had empty set into point, that gave me point into M, that picked out a preferred element. On the other hand, the multiplication, that's 2 points mapping down to 1 point. And then that gave me M cross M mapping back down to M. So I'm seeing the whole thing, and the conditions of commutativity was the fact that there's actually a unique map from the 2-point set to the 1-point set. So if I precomposed with the twist on the 2-point set, that was the same thing as the map I got. That's that my multiplication is commutative. And if I think of associativity, that's saying break up the 3-point set in a couple of different ways and map it down to the 1-point set. Well, I don't care what happens. Again, there's a unique point to there's a unique 1-point set and a unique map to the 1-point set. And so then I get the same thing no matter how I do it. This is actually, in some sense, the approach that that Lurie takes when he's talking about a symmetric monoidal infinity category. That I'm describing what Lurie calls the active morphisms in this. Really, they're the ones that came from maps of finite sets. And that's the way to think about it, that they're the ones that Siegel tells us, these are the things that I use to describe the multiplication and the unit in my context. So I'm doing the same thing, but now I have more notions for what do I mean by point. I need to tell you, what do I mean by all of the different flavors of point? So that's all of the orbits, G mod H. And then I have maps that connect all of these. I have the fold map, G mod H, disjoint union G mod H, back to G mod H. That endowed each of these with a multiplication. And then I also have transfer maps, but the obvious diagram that I get from the disjoint union of 2 things folding down to the disjoint union of 2 things that it mapped to folding down, I get a commutative square. And that just says that all of my transfer maps are maps of commutative monoids. So it's just recording the same thing that I saw from sort of that Siegel perspective. And so now I want to try and give a sense for how to put all this together. And so I want to have a coefficient system of symmetric monoidal categories. And before I get the question, I'm going to ignore all 2 categorical issues. So there's a lot of lying that's going to happen. But so I'm giving vibes. So thank you. I feel supported there. I thought about having like a whole thing and staring right at the owl and being like, I do not consent to this being recorded. But But then Niall reminded me that actually the opt-out thing is sent to me via email, and we all know that I don't read email. On the part of the organizers. It was a trap that they didn't even have to cover with sticks or something. I just dove right in. Anyway. So I have a coefficient system of symmetrical categories. So in this, think about it as a functor from the orbit category op, but now into something like symmetric nodal categories. And then there's a prototype for that I want to keep in mind always as my main example. And that's the coefficient system of finite something sets. So this takes the orbit G mod H to finite H sets. And it's supposed to be a coefficient system. Well, the maps that correspond to restrictions are restrictions. So if I had an H set, I can restrict it to a K set. That's pretty straightforward. The symmetric nodal structure I want to use on this is disjoint union. And the restriction map is compatible with that in that the restriction of a disjoint union is the disjoint union of the restrictions. So in this case, what I want is a map, and this is just sort of the level-wise product of the coefficient system. So it again gives me a coefficient system. And then I'm asking it to be essentially bilinear, and I never remembered the right term for this. And so, but by this I mean I want this to be symmetric monoidal in each of the variables when I hold the other one fixed. So it's exactly the bilinear if my notion were additive. And that actually puts a lot of constraints on this. So it means if I had a finite H set T and some object in C of H, well, it says that the empty set has to act as empty set, norm to empty set of anything has to be the symmetrical unit in C. Norm of point has to end up being point, or the identity. There are a lot of constraints that I end up seeing, and the norm of T is always a nice symmetric monoidal operation on C. So the prototypical example for this is actually a symmetric monoidal Mackey functor, so a Mackey functor object in symmetric monoidal categories. And this is going to have transfer maps that I'm going to write as norms, sort of essentially using the same notation that Mike Mendel did yesterday, where now I have these multiplicative transfer maps, multiplicative in the symmetric modal sense, from my symmetrical category C at G mod K back to C at G mod H. And then this gives me the initial kind of structure that I wanted by considering the composite of restrict down to K and then transfer back up. So if you're familiar with the Burnside Mackey functor, so this is the symmetrical unit for the tensor on Mackey functors that I will talk about a little more soon, then this is the Mackey functor whose value at G mod H is the free abelian group, or it's the group completion on finite H sets. So it's the free abelian group on the isomorphism classes of orbits, H mod K, as K ranges over the subgroups. And every Mackey functor is automatically a module over this, and the multiplication by some element, H mod K, is exactly given by the formula restrict down to K and then transfer back up to H. So this is, you should really think of as saying, this is just the usual action of the Burnside ring, but at a categorical level. The only way I would make sense of multiplying by H mod K is restrict and then transfer. So the main examples that I want to keep in mind are what you might call the G Cartesian one. So here I'm going to have, I probably need some conditions like to guarantee that my restrictions have a right adjoint, but assume that my restrictions all have right adjoints, then I can build a symmetrical Mackey functor where the symmetrical norm maps are the right adjoints, and those are the ones I'm going to use. In this case, the symmetric monoidal structure is given by Cartesian product, and the right adjoints, being right adjoints, commute with limits, and so they are symmetric monoidal operations. And then the restrictions I insisted on being symmetric monoidal. And so the prototypical examples here, coefficient systems, where I use the restriction maps and co-inductions, G spaces with, again, Cartesian product and co-induction, representations gives me another example of this, where I could use restriction and co-induction. It's kind of only one term we're going to keep using for this. The right adjoints is sort of always called co-induction. Other examples, I could use, say, ring objects in representations. So commutative rings with a G action, and then its usual restriction and co-induction, because for all of these, the limits are actually formed in the underlying category. So I keep running into this like kind of frustrating point. Here, the G co-Cartesian, it works a little better in that I get to say different words. Here, my symmetrical structure is again going to be disjoint union, but now I'm going to use the left adjoint to the restrictions. And this is going to commute with disjoint union because left adjoints commute with co-limits. And then I get a sort of a different, nicer structure. The coefficient systems with induction, topological spaces with induction. And if I did this now for rings with H action as the value, commutative rings with H action for G mod H, then the left action here is tensor induction. So I tensor together a bunch of copies of the ring. So in this case, it starts to do something different. And in fact, on Tuesday, I had a slide that said that, oh, if I look in coefficient systems, then the forgetful functor, the restriction, had both adjoints. And I spent a lot of time stressing that I want to look at the right adjoint because it actually does interesting things at the fixed point level, and the left adjoint didn't. So the co-Cartesian one, it's sort of, in a lot of cases, it can be fairly boring, but we're going to see that the structure that we want to build makes them all coincide. So it's sort of where I want to go. Okay, and then a few more bookkeeping pieces. That G symmetrical functor is exactly what you would think it would be. All of the usual adjectives that you would put before symmetric monoidal, you just copy, like strong, isomorphisms, lax, just have a map, like up, do things backwards, like the usual things, you just copy them and it goes through. The key thing is this property that it essentially commutes with the norms as well. If I was coming from a G symmetric monoidal or a symmetrical Mackey functor, then it's exactly the thing you would expect. It's going to be a functor of Mackey functors that's symmetric monoidal level prize. The homotopy coefficient systems give me a nice example of this, where I'm using actually the Cartesian monoidal structure, because maps into a product is the product of the maps. This doesn't work if I'm using the G co-Cartesian one, because I have the disjoint union that doesn't play nicely with these. All right. So now, once I have a G symmetrical category, then an object at the G mod G level, so an object at the fixed points, gives me, well, first it gives me sort of a diagram of objects, one at each levels. Oh, sorry.
Yeah, sorry, just the definition in this slide before, do you want F to come with the norm or just?
Pardon?
Do you want the functor F to come with the norm or just the existing one?
So it's going to depend on what adjectives I attach to it. If it's strong, I want to commute with the norm. Then I want this to be an actual isomorphism. But I could just ask for the lax version, and then I just want the map.
Right.
I guess for legs you want the map the other.
I want them at the other way. Yeah. Thank you. So I guess this is the Oplax version. I have after each of the talks found all of the typos. It's like an opportunity for self-castigation. And then and so I've been fixing them, and they're actually all on the internet, and so I will make the links more prominent. So I'll fix this one too. Thank you. All right. So once I have an object at the fixed level, then this gives me a diagram, so a sort of constellation of objects. Because an object at the fixed level, since point was terminal in the orbit category, maps out of it actually sort of flowed down into all of the other pieces. So at level G mod H, I just restrict that object to H, and that gives me an object there. So I can think about this then as actually a functor now from the orbit category up into my coefficient system. Now, once I had this, I could hold that object fixed, that's my x bar, and just consider the corresponding functor from finite something sets and isomorphisms now into C. And I'm going to take a finite H set T to the T norm of the restriction to H of X. The G commutative monoid is just an object at the fixed point level, together with an extension of this functor that I wrote right there over all of finite something sets. So again, at each of the levels, I have essentially a commutative monoid, because I'm using the symmetric modal operation. In fact, it's not essentially a commutative monoid, it's exactly a commutative monoid. And I have these norm maps that connect I can either think of it as connecting the values at different levels, or I can think about it as sort of an internal structure at each level. I have a map from the G mod H norm of M back to M for all H.
Mike, so when you say extension, you also require that it is symmetric model, right? Like you take like co-products to products. G commutative monoid, they want to right assign.
So this one, what the underlying point set functor is, or so the underlying functor on objects is shown by this, which is symmetric monoid.
Okay.
Yeah. And then so what I'm asking is then that basically the only difference between these is what's happening on the maps.
Mhm.
The finite something sets and isomorphisms is a wide subcategory sitting inside finite sets. So I've specified the functor's value on all of the objects. What I haven't specified is some of the additional maps. And the maps that I'm missing are exactly inclusions, which correspond to putting the unit in various slots, or fold maps, which correspond to the multiplications, or the maps on orbits, which correspond to the internal norms. Other questions? This is literally, I'm just taking the thing that we saw with oh, this shouldn't have been, I copied this diagram, obviously. This shouldn't have been, that should have been a C, not quote. Sorry. A lot of changes for this one. Now, one of the key features that showed up in transfer systems and infinity things and the indexing systems, one of the ways that Andrew and I think we were sort of on the right track for looking at this. There's this incredible internal consistency between these, that when I look at the finite O sets, when I looked at the indexing category, if I restrict that from G back down to some H, that exactly gave me the finite H sets corresponding to the restriction to H of O. And so I can think about that as saying, given any transfer system, then finite O fin GO actually gives me its own symmetric monoidal coefficient system. That's a sub-symmetric monoidal coefficient system of finite something sets. And so that is what I mean here. the value at G mod H is just fin H. And now an O commutative monoid, it's basically the same thing as a G commutative monoid, but I'm not asking for all of the possible maps. I'm only asking for norm or transfer maps structured by O. So it's exactly the thing that I would hope. And the key examples here are that O commutative monoids in coefficient systems, this is just a Mackey functor. An O Mackey functor, excuse me, I should have said O. I said a lot of, a lot of typos in this one. All right, there's a couple of examples of coefficient systems that sort of should have come up earlier in my lectures, but somehow didn't. One of which is transfer systems have both an initial and a terminal object. If I think of them as a partial order that's refining the usual inclusion, well, given any set, there's actually an initial partial order on that set. It's the one where I say the only thing something is comparable to is itself. And that's reflexive because I said it's comparable to itself. It's symmetric because the only thing I have to check is it itself? It's transitive because I just need to check if I have three things and they're all the same, are they all the same? And yes. And I didn't have to worry about the order, in fact. It's even better, like it's everything I would want. So in this case, if I apply this to the set of subgroups of G, then that gave me a perfectly good transfer system. Now you might ask, well, I never said anything about conjugation or the restriction condition, but these are very easy to check in this case, and I invite you to do it yourself. It's a useful exercise as you start to work through these. So when I do it in this case, this one, which feels like a very, it's the initial example. So it gets the super judgy term trivial attached to it. I kind of actually prefer to call this one a combinatorial one because it's the same thing that structures what you might call a combinatorial E infinity operad. Given any symmetric monoidal category or symmetrical infinity category, any of this, the thing that it's structured by is this object. It's a purely combinatorial statement that doesn't have any interaction between the group or ambient context and this symmetric group. So for this one, what does it actually mean to say that I had this O commutative monoid? Well, the thing I need to ask is, what's that fin GO for this? And the transfer system, the dictionary that says, take my transfer system, the first thing I want to do is think, okay, given my transfer system, how do I describe that fin GO? Well, a map is in fin GO if when I take any point in the source, it has some stabilizer. And then the image of that map in the target, that has a stabilizer. And because of equivariance, stabilizers grow. That's just it's literally like a statement of equivariance. So I now have a comparison. One subgroup of G sitting inside the other subgroup of G. So my map between two finite G sets is in fin GO if and only if for every object in the source, the corresponding map on stabilizers is in my transfer system. That's the whole thing. So here, I'm saying that my transfer system is only identities. So the only comparable things in my transfer system is that something is comparable to itself. Translated over in the other stand. That means for every element in the source, the map on stabilizers from that to the target had to be an isomorphism on stabilizers. That tells me, or the identity on stabilizers, excuse me. That tells me what those maps look like. They all look like fold maps. I never see things that map between different orbits. It always just looks like a fold. And so these this is why I was stressing again, these are sort of something that shows up in a really kind of universal way, in a purely combinatorial way. This is just an ordinary commutative monoid. And that's true in any context I would write down, that it's always just the ordinary commutative monoids. At the other extreme, and it didn't show up on this slide, is transfer systems also have a terminal object, and the terminal object is just sub G itself with the usual inclusion. And there, the O commutative monoids tend to be sort of those are the G commutative monoids, it's the richest structure, and there I get the ordinary mapping.
You want in that example to say that it's a coefficient system of commutative monoids.
Yeah. In all of these, I'm actually kind of blurring the distinction of what my target category is. I could have in all of these said that coefficients was actually coefficient system of sets. And then I would have rebuilt exactly the coefficient systems of commutative monoids. For linguistic or like expository ease, didactic laziness, I was doing coefficients of abelian groups, in which case it's actually no additional data. And that's kind of a, yeah, it was bad form on my part. Okay, so now I want to stress sort of two little things and then move into the multiplicative case. First, and this is actually something that Mike talked about in his talk, that when I had my context or my categories of spectra and they were indexed by some n infinity thing, if I had an admissible G mod H, or as I'm writing it as a transfer, K to H, that should have been that should have been an H to G, whatever. These and these should be the same. But the key thing is that if I have the transfer, then the corresponding norm on my commutative monoids is actually the left adjoint. Okay, if I didn't have any covariance, then this is a statement that you're familiar with. I know if I'm looking at something like abelian groups with tensor product, then the coproduct of abelian groups with tensor product is the direct sum. That's sort of an interesting thing. But the moment I switch to commutative monoids for tensor product, the coproduct in commutative monoids for tensor product is the coproduct of commutative rings is the tensor product. So it's a very general categorical fact that if I'm looking at commutative monoids for some symmetrical operation, the coproduct in that is the symmetric monoidal product. This is just the G twisted version of that. The left adjoint, so the twisted coproduct indexed by G mod H is the left adjoint to the restriction. And so in this context, if I'm looking at a G symmetric monoidal category and I'm looking at the G commutative monoids in it, then the original G commutative, the G symmetrical structure that I had is automatically G co-Cartesian on the commutative monoids. So I call this ambidexterity because if my G symmetrical category was coefficient systems, the G commutative monoids are Mackey functors. And this rebuilds for me the familiar sort of Frobenius relation that the two adjoints, induction and co-induction on Mackey functors, agree. If I was stable, if I were a real topologist, then it's like a weird Pinocchio moment. I need a minute for myself. Then I would be again saying that in G spectra, the restriction from G spectra to H spectra also has both adjoints. And the hallmark, exactly as Mike pointed out, the hallmark of this is that both of those adjoints actually agree. That this is a restatement of the Wertmüller isomorphism. That I had a map from the left to the right because I'm pointed, and that map is always an equivalence in these, or in algebra, it's always an isomorphism, once I'm in the G commutative monoids. Okay. So I want to now switch to the multiplicative version and rebuild that, because I spent a lot of time last time talking about Tambara functors, and the punchline is going to be that Tambara functors, the G commutative monoids in Mackey functors, once I give it the right G commutative monoid structure.
It's such a beautiful diagram,
What did you say?
such a beautiful diagram.
Oh, really? Okay, thank you.
I want to send this to Christy.
Oh, please do. Yeah. Say hi for me. Okay, so I need to describe for you how to build a two kinds of operations. First, I need to describe how do I build the tensor product on Mackey functors, which is going to be building my ordinary commutative monoids, which are sometimes called green functors. And then second, I need to build the norm maps in this. And so the tensor product is perhaps the first one that I might write down. Here, I have a Cartesian product on my Lindner category, and I adorned everything with an O, because then I could do this in one slide rather than in two, where I would have just copied everything, and then I would have found that I forgot to make the necessary changes half the time, and then I would have felt really awkward, and then I would have spent time talking about it. So instead, I did it in one slide. And here, the left map is the Cartesian product, and since the Cartesian product is the product, it's a limit, it's going to commute with other limits, like say, pullback. And that's what I needed to know that this actually gave me a functor on the Lindner category. I'm just doing this sort of object-wise products. In fact, the Lindner category becomes sort of this semi-ring category. And then the top map is I just do the external tensor product, the one that takes a pair of things in the source, ST, and sends it to evaluate M at S and tensor that with evaluate N at T. And then I left con extend. And the left con extension is my map here that's called the box product. And I don't know why the box was rendered in this way. I've given up. I mean, actually kind of structurally, but in this case, in the slide writing is what I meant. So here, which is like, okay, we're going to talk about this later because I think you might have just fixed something for me. Thank you. Now the norms I'm going to define in a very similar way, and this was done in Kristen Mazur's thesis. It was done in Rolf Hoyer's thesis. The two of them handled the case where O was actually all finite G sets, so the genuine case. And then David Chan did this in the incomplete Mackey functor case. And so in this case, for this statement actually to be true, what I want to do is I actually need co-induction, which again, being a right adjoint commutes with pullback, so it is going to give me a functor. Co-induction, I need it to actually land here. But that's a statement about co-inducing induction, preserving the things that I'm allowed to transfer along. That's the compatibility condition. So this lands here is exactly the statement that G mod H, that the multiplications that I'm looking at, that G mod H is compatible with O in an additive sense. And then I can left con extend along co-induction. And that's my norm. So these formulas are really helpful. I mean, left con extensions are great. I mean, it gives me an exact description, but it's sometimes a little hard to unpack this. So I want to do it in two cases to sort of think through it. For the box product, here's sort of a heuristic for how to do it. The first thing is you guess, like, what's the actual tensor product? Well, I just take the tensor product level-wise, and that's wrong. But it's not irreparably wrong. So I can start with that as a building block. But now I've written down a coefficient system. I lost my ability to control the transfers once I did this. So I'll formally put in the transfers. I use the left adjoint from coefficient systems back to Mackey functors. And now I've double counted a bunch of the transfers because I had a bunch of things that already were, and so I put in the relations that are sometimes called Frobenius reciprocity, because in representation theory, this is how it shows up. And then it just says that if I have some class and I tensor it with a transfer, then that whole thing is the transfer of the restriction of the class times B. The two T sub Fs are actually playing different roles in this as the way it's written. The one on the right-hand side of both of the equalities, this is the transfer in the original underlying Mackey functor that I was tensoring together. The one on the left-hand side is the formal transfer that I added in as part of step 2. Now, because I defined these via left-con extensions, it's actually super easy to compute them on representables. Left-con extensions of things on representables is just do the corresponding functor on the representing objects. So when I boxed two representables together, and that could have been the AOs instead, and I would have gotten the same thing, then it's just the representable for the Cartesian product. So now because of this, and because I'm looking at the box product, which actually has a right adjoint, so it is a left adjoint, which means it commutes with all colimits in each variable. This second part, the part's titled key example and left adjoint, also gives you secretly a formula for computing the box product of any two things. Write them down as a quotient of representables. Tensor those two things together. I get a little chain complex. And all the pieces in the chain complex are things I know how to take the tensor product of because they're representables. And then I just write down the answer. So it's in practice, it's very doable. So with that, let's do the norm. And here, same thing is basically true. On representables, the norm is defined by a left-con extension. So it's the representable for the value of the functor on my representing object. So the norm from H to G of the representable at T is just the representable at maps from G into T. Now, the norm isn't a left adjoint here, but it does commute with sifted colimits. So you can think of it as like the things that show up in a simplicial diagram. These are sort of the prototypes of simplicial, of sifted colimits. So coequalizers are not, but reflexive coequalizers where I have a zeroth degeneracy, that is an example. And so since it commutes with sifted colimits, well, I can't just write down my thing as a quotient. Instead, I have to write it as a sifted colimit, so as a reflexive coequalizer, and then I can get the whole thing. So here's sort of a warped example. I have a chain complex. This is like a, I don't know why I'm going into this. This is a resolution of Z mod 2 as a by 3 Z modules. Okay, great. Abelian groups are Mackey functors for the trivial group. And so here I'm looking at a Mackey functor for the trivial group. This is just a chain complex. That's not going to be good because this is a colimit, but it's not giving me a sifted colimit. To make it a sifted colimit, I have to add in a second copy of Z here. That's formally the image of my zeroth degeneracy. If you think about it as I'm undoing the Dold-Kahn correspondence, I had a chain complex of abelian groups. I build instead the simplicial abelian group. And now I have something that I can hit with the norm. This is something that's represented, in this case, by the 2-point set. I know what the norm of this is. It's maps from C2 into the 2-point set. I know what the norm of this is. This is represented by the 1-point set. It's maps from C2 into the 1-point set. It's just they're represented by a point. And then you can also, without too much trouble, work out what these maps are. And that gives me a formula for what the norm looks like here. Now, what Kristen and Rolf showed are that if I look at the G commutative monoids in Mackey functors with the box and norm G symmetrical modal structure, this is exactly the data of a Tambara functor. And then David Chan showed that if I look at the OM commutative monoids in my OA Mackey functors with, again, the box product and the norms, then this is the same thing as a bi-incomplete Tambara functor. And so just restating this, to give myself a Tambara functor, this is the external version, finally, of a Tambara functor. It's to give myself a Mackey functor together with an extension of T goes to the T norm of R to a functor on all of finite G sets. And it's the same thing that I've seen again and again, but it sort of packages it all in sort of one fell swoop. Now, there's some really nice consequences. The first is the sort of ambidexterity type result, although here it's not by any means ambidextrous. This is actually more a sinister result in that I'm describing to you the left adjoint. So the Mackey norms are the left adjoint to the forgetful functor on the O commutative monoids. Now this is really nice, and it's a theme that I hadn't had a chance to sort of ramble too much about yet, but it's something that says that I have this algebraic object, and I have the left adjoint on it is something that I can compute in the underlying additive category. I'm just doing the ordinary norm in the additive category. So the example that I drew in green, this is the start of the free green functor on something in the underlying. This is the left adjoint in commutative green functors of the polynomial ring in one variable. This is not some functor on Mackey functors applied to the polynomial ring in one variable. It's a functor on green functors applied to the polynomial ring in one variable, not a functor on Mackey functors. That means it's very hard to compute. It's the kind of thing like you basically are probably going to have to trust me that this is the right thing, because you have to sit down and work through it, as opposed to saying, oh, I just take the norm. And that's something that I know how to do. So it's this concept that's becoming increasingly clear that it's like the right thing to be thinking about, that I'm able to actually compute a bunch of kinds of colimits instead in this underlying category of Mackey functors, rather than lifting all the way to the algebraic story. Yeah, I just rambled about it. I said that. All right, so let me give you an example, an application, and the application is to rational Tambara functors. So if I rationalize this, this also lets me mention that like a lot of what Mike talked about on yesterday, I can redo in the algebra. And in this case, the role of geometric fixed points. Thank you. The role of geometric fixed points is played by evaluate my Mackey functor at G mod G, and then mod out by all of the images of the transfers. In fact, this is also what I would do in G spectra, that I would probably think of them in the other order. I would think of the thing where I formally killed off all the image of the transfers. That's take the cofiber of the map, EP plus tensor X back to X. And then I would take fixed points, which on the thing where I killed off all the transfers, the fixed points was actually an equivalence of categories down to abelian groups, so it didn't really do anything. This is what Mike was talking about when he said that the geometric fixed points is actually more a left adjoint. It's a localization where I've killed off everything coming from the underlying. And then I did a step that was pain-free. It was taking equivalence of categories. So I do the same thing here, where I'm doing the geometric fixed points in Mackey functors, and this has the exact same formal properties, that if I take the geometric fixed points of the norm, that's the same thing as doing the H geometric fixed points, and the geometric fixed points is symmetric monoidal for the box product, but it took the box to the tensor of the geometric fixed points. So I'm attributing this theorem to Greenleaf-May and also to Strickland, because the Greenleaf-May part is, I'm restating that one here. That to give myself a Mackey functor, well, to give myself a Mackey functor, any Mackey functor gives me a functor from finite G sets and isomorphisms into Mackey functors. That was M goes to, T goes to the T norm of M. And then I can post-compose with the geometric fixed points. So that now took M to the functor, T goes to the geometric fixed points of the T norm of M. The Greenleaf-May result is that this is an equivalence of categories. And so I can completely understand rational Mackey functors by instead thinking about these diagrams of rational vector spaces. And the tensor here is just to remind me that I'm taking the disjoint union in finite G sets to the tensor product of rational vector spaces. Strickland then said, this promotes to saying if I'm looking at the Tambara functors for G, then that corresponds to exactly as we've seen a bunch of times, the symmetric monoidal functors from finite G sets into rational vector spaces. Or if you prefer, functors from the orbit category into rational commutative rings. So I can sort of see this in a really clean way from this perspective. Okay, so let me put on a topologist hat. Luckily, Mike told you all this. So so Mike pointed out yesterday, we also have this a lift of all of this to spectra. So I have the norm functor going from H spectra to G spectra. I use superscripts on my equivariant categories to remind myself that I'm looking at the fixed points of the underlying G space of maps that show up everywhere, as opposed to the orbits. So I have a functor from H spectra to G spectra. Its properties are that it's strong symmetric monoidal, it commutes with sifted colimits, and the infinite suspension spectrum, I see, I choose to ignore. The infinite suspension is actually a strong G symmetric monoidal functor. So that's why I actually brought it up earlier. So because of this, I can actually compute a bunch of things. You can work out that the norms of the representation spheres are the induced representation spheres. You can work out that if I have something that's connective, then the norm is also connective, and that pi zero of the norm is the norm of the pi zeros. And then I have that when I'm looking at O algebras in spectra, that the admissible sets exactly structure norm maps for this G symmetrical structure. And another way to say it is once you build the machinery, that O algebras are exactly the O commutative monoids in spectra with tensor and these norms. As a really nice example, and I like this because it ties in, I think, with what Mike was talking about yesterday. If I had an O algebra in spaces, then because the infinite suspension is strong G monoidal, that told me that the infinite suspension of it is actually an O algebra in G spectra. And then how do I understand the norms in the O algebra in G spectra versus the transfers in the O algebra in spaces? They're the same thing. This is, if I have a group ring, the product in the group ring is the addition in the group that I rung. Anyway, it's that, but in the twisted version. No, I'll stop here.
Well, how does all this fit with Stefan Schwerner's global lecture?
There's a great paper that appeared on the archive a couple of weeks ago that answers that better than I ever could.
Anyone else?
Yeah, thank you.
Well, and let's thank Mike again for his fantastic work here.